Okay, so welcome to this another session of structural analysis. We will be stability, equation of equilibrium, and stability. We were discussing, I think so. I'll just quickly recap what we did. I told you that the first starting point. Okay, can I have your attention, please? Yeah? Okay, so we discussed what determinate structures were, indeterminate structures, and then how stability is relevant to our determinacy and indeterminacy. Okay, the determinate structure we said are those structures in which you have got number of available equilibrium equations equal to number of unknowns. Okay. So, number of available equations are the equilibrium equation depending whether you have a 2D structure or a 3D structure. Sir, excuse me. Thank you. So in the case of 2D structures, we have essentially three equilibrium equations, two related to forces and one related to moment. Okay. Now, if the number of equations, number of available equations, if they are more than the unknown reactions, then it is, if the number of available equations are more than the number of available reactions, then it is unstable. Why is it unstable? Because all the equilibrium equations won't be able to, won't be satisfied. Okay, so that's common sense. If all your equilibrium equations are not satisfied, then in that case, it is an unstable structure. Okay, so you must have the number of unknowns at least equal to number of available equations. Okay, now if the number of unknowns are more than the number of available equations, then in that case we call that indeterminate structures. Okay, in your structure analysis 2, you will see how we tackle that problem, because obviously if the number of unknowns are more than the equilibrium equations, so you need more equilibrium equations, more equations. And how do you get those equations? That is from your elastic curve, the behavior of your elastic curve. So for example, like I just give you one example before, if for example, my elastic curve is like this. Excuse me, sir. Can I? Please? Okay. Thank you. So I'm saying, imagine this is our elastic curve. So this is a prop cantilever beam. Okay, why do I call it prop cantilever beam? The elastic curve of prop cantilever beam, because this is a fixed connection and this one is a pin connection. Okay, so the property of my elastic curve is, so imagine my left hand is point A and my right hand is point B. Okay, so at point A we have to work out the compatibility, what is called compatibility equation, or the equation of the elastic curve. So what is the equation of elastic curve at point A? The deflection is 0 and the rotation is 0. Isn't it? Yes. There is no rotation. However, at point B, we have rotation is unknown, only the deflection is 0. You will have rotation. Look, rotation is 0. What is rotation? Moment. Yes, but I mean, in the case of, for example, if I have got a beam, okay, this is my prop cantilever beam, and what I was showing, the elastic curve, so, or the deformed profile of this prop cantilever beam. Yes? So what I am saying is that rotation over here is 0. Why? Because if I draw a tangent, that tangent doesn't move. It stays at the same point, isn't it? Yes. However, over here I have got some finite rotation. This is the rotation. The rotation. What do I mean by rotation? How much this deformed curve make with the original axis of the beam. This is the original axis. The black is the original axis. When you apply load on it, any sort of load, it will assume a profile, this sort of profile. Do you understand? This is the deformed profile. Yes, sir. So this is like I have held this tightly in this hand, so I don't allow any rotation. But this is rotation. So this rotation is allowed. Yeah. So over here we will have deflection 0, but there will be a finite rotation. And over here we will have both deflection and rotation equal to 0. So using this property, you can develop another compatibility equation and you can solve your unknowns. This you will do in detail in structural analysis 2. Okay, but that's not so. So after determinate and indeterminate structures, we have stability. In stability, we have to make sure that our available unknowns are at least equal to the number of available equations, a number of equilibrium equations. Okay, not the available equation, number of equilibrium equations. So if the available unknowns are more or equal to the number of available equilibrium equations, then we have a stable structure. And we discussed, like in case of unstable structures, what do we have? We have the structure not satisfying any of the equilibrium conditions. Okay, why do we call it unstable? Why? Because some of your any of your equilibrium condition would be violated. A force in a certain direction will be violated, or a moment will be violated. Okay, so that's why we call it unstable. So we had a discussion about that. Now, one thing in stability which I wanted to discuss. Okay, so in stability, in the case of stability of structure, we have we can have two scenarios. One is partial restraint. You have a partial restraint, or you have improper restraint. Okay. So what do we mean by partial restraint? By partial restraint, we mean that you have, for example, a structure like this, and you provide a internal hinge in the middle. This becomes unstable. Okay? So this is something which is called partial restraint.
But the reactions are equal to equations.
No, the reactions are not equal to equations. How do you say reactions are equal to equations?
What reactions?
What? There are how many? This is, you have got 3 unknowns.
4 unknowns. Then one on this one is.
This is a pin. So you have got 4 equations. And the number of unknowns are 3. So this is an unstable structure. 3.
If we have pin on both sides.
Sorry?
Pin on both sides.
What do you mean pin on both sides?
Pin support on both sides.
Over here? Okay, so if you have a pin support on both sides, then what will happen? You will have how many reactions?
4 pin on both sides.
Okay, you have got, okay, so this is also a partial. Let us do this one and then we'll put pin on both sides. If you have a roller support like this, so in this case again, you have how many equations?
2 equations.
You have got the equations stay the same. You have got 3 equations, but the available unknowns are 2. Okay, so the summation of effects will never be satisfied. So this is an unstable structure. Okay, because this will start rolling. Now, if you say if we have a structure having a pin on both sides, so this is a stable structure.
Hinge in the middle.
Okay, so yes, if you have a hinge in the middle, Okay, so in this case we have four reactions, four, and how many equations?
Four equations.
So we have four reactions and four available equations. Okay, so this becomes then stable. No, this, why is this unstable? Because if someone stand on it, this will start rolling. So obviously you can't stand on it. Okay? So you can't stand on it. Why? Because this will start rolling. There is nothing to stop this movement. I mean, it will start moving in this direction. So there is nothing to stop it. That's why it is unstable. This one is stable. Why? Because these two pins are providing restraint. So although this is like a link, you have provided one link, you know, a link of a chain. So this is a link, but it is stable. Okay? Do you understand my point?
Yes, sir.
Yeah, so that is, so this is not a partial restraint, this is a stable structure.
When some force is applied in the middle, it will cause some movement at the end, and pin support cannot.
No. What do you mean? If you apply some load over here,
Yes, sir. Yes.
Okay, if you apply some load over here, then what will happen?
The moment will be produced at pin support at.
Why? This pin support can never take moment.
Yes, sir. That is exactly what I am saying. Then what will counter that?
Inch.
You have got, what will counter? This is the same thing. Look, in the middle, you can have moments. You can have moments in the middle, but you can't have moment over here.
Yes, sir. That is exactly what I am saying, sir.
Yes.
This load will produce moment, and there is nothing to counter that.
No, but how do you say the moment is balanced? Whatever moment it produces is balanced. The overall system moment would be balanced. Summation of all moment would be equal to 0. So it is more producing moment, yes, but at this section, at this section, at this section. But if you draw a free body diagram, okay, so that moment will be balanced. You don't understand my point. Like for example, I have okay, so what will happen? You will have a moment over here. Yeah? So this reaction, this time this, you will have a moment. Agreed? And that moment will become 0 when you come over here.
Yes.
So
The moment will balance.
So the moment will become 0, or either you won't have moment at all.
Yes, sir.
In this case, if you put your load over here, for example, so what will happen?
It will still balance, sir.
How can it be balanced? I mean, if you put your moment over here, what will happen? If you put your load over here, right, you will have some moment. Yeah, that moment. So this time, it would be this force time this lever arm. Okay, but as you go over there, what will happen? That moment will start decreasing. Why? Because you will have this one cancelling the effect of that, and the time you reach over here, you will have 0 moment. Okay. In a case if you have load over here, then what will happen? If you have load over here, then
it will be that arm times the reaction.
Sorry?
It will be equal to the reaction into that moment arm.
Yeah, so it will be equal to your reaction times moment arm. Yeah, but essentially you will have that moment. So the moment would normally become 0. Okay?
दोनों मूवमेंट्स क्लॉकवाइज ही हैं, मतलब वो भी मूवमेंट क्लॉकवाइज है, जो फोर्स लगा है उससे भी क्लॉकवाइज है, उसके सपोर्ट भी तो है.
So I didn't get you.
I mean the force at the end of
Look, let us do it you have a
अली तू ट्रांसलेटर बन जा इस क्लास में, इस क्लास में तू ट्रांसलेटर का काम कर।
You have a load, imagine you have got load like this. Okay? Now, this will have a component in this direction and a component in this direction. So, this one, half of it will go there and half of it will come here. Okay? Now, what will happen? The deformed profile will be something like this. Okay? This will get deformed. Yes? And you will have excuse me, can I have a silence please? Thank you. So you will have a reaction, say imagine R1, yeah, and that R1 will be equal to R2. Sorry, this will also be R1 because summation of fx, sorry, this will be R2. You will have R1 and R2. Okay? Now, P by 2 times this, yes, minus R1 times this. So that R1 times this distance. Okay? So that moment, so when you come over, so there will be moment generated by this, but that will be counteracted by this reaction. And it will become 0 when you come over here. So this is, in other words, the geometry of this will change because it's like a link. Okay? This is not a small displacement problem then. It's this will be a finite displacement. Normally when we talk about structures, we say that it is a small displacement, but its geometry will change. Okay, so that if you take this as a small displacement problem, then it doesn't work. Then, I mean, it's small displacement wise, this wouldn't work. You have to go for a large displacement, which is in reality true, because you will have, this is like a chain. So you put any load on it, chain will deform, isn't it? Yes. These are two links of a chain. So that's what. Yes.
सर आप जो मूवमेंट ले रहे हैं या दरमियान वाले हिल से ले रहे हैं या पॉइंट ए से ले रहे हैं?
Wherever you want to take.
सर लेफ्ट साइड से लेंगे तो कपल नहीं बन रहा है.
What? This times this. Yeah, P by 2 times say L by 2. And R1 times whatever this distance is.
सर वो तो पॉइंट से गुजर रहा है ना लेफ्ट
साइड.
The movement generate नहीं करेगा.
What? Sorry?
R1 will not generate the movement because it is going through the center.
No. We are taking moment about this point from the deformed profile, not from the undeformed profile. We have to take it from the deformed profile. So R1 will generate. And in reality, it is always corresponding to a deformed profile. However, in this class, we will assume because of the small displacement, we will consider it from a undeformed profile or initial profile. In your MOS, you have done beams. Okay? You have assumed that the displacement is very small. That's why you consider the axis the same, isn't it? You take your moments, everything corresponding to this axis. But in reality, it's not so. I mean, there is some difference, but that is very insignificant. That's why it's a good assumption. Okay? It's a good assumption that you consider. But in this case, particularly in this case, this is like a cord. Okay? So cord will, if you put load on a cord, it will deform. And that will be a finite deform which you can visually see. Okay? Which you can visualize. So that's why it's a finite. What is a finite displacement? common sense wise, it is that displacement or that deflection which you can visualize. Okay, and this one clearly you can visualize.
Yes, sir.
So that's why we are taking it like that. Okay, so this is our partial restraint. Okay, then we have, after this we have sorry. Okay, then we have improper restraint. Improper restraint. What does that mean? Imagine we have got a beam whose supports look like this. Okay, so you put a load, so there are 3 rollers. This is inclined like this, this is inclined like this, and this is inclined like that. Now what happens is that all your reactions, they meet at the same point. If your reactions meet at the same point, what does that mean? In engineering mechanics, if everything meeting, huh? No, what does that mean? What do we have? Yes, moment is 0, isn't it? Because there is no resultant force which will cause movement about this. This is such a small point. Everything, all the reactions are merging at one point. So, whatever resultant you have, okay, that will have 0 lever out. So that means that your reactions won't satisfy which equation? The moment equation. So you must make sure that your support don't meet, all of them don't meet at the same point. That is, okay, so you should never have this thing. So if I have a load applied at some eccentricity, okay, or in other words, at some offset from one of the support, okay, then this can cause it to rotate, okay, and this will start rotating. Yeah, this beam will start. Why? Because the reactions won't give any resisting moment. Do you understand my point? So this is called improper restraint. You will always avoid this sort of restraint. Okay? Is that okay? Yes. Any question? Please ask. Yes?
Is this structure subjected to improper restraint in this figure?
This is improper. Yes, it is improper.
When all the reactions meet at a point?
When all the reactions are meeting at a point, yes. You look for a stable structure. A stable structure reaction will not meet at the same point. Okay? The resultant of all the reaction will be at some distance apart. But in this case, it will meet at the same point. Yeah. Okay, should I rub it off? Yes? Okay, so this was your first chapter. Okay, so I would like you now, guys, I would like